Hello and welcome to our lesson on limits and direct substitution. Up until this point, we've been doing limits from a graph. We've done limits from a table, and now we're going to explore direct substitution. Now, direct substitution is very nice as long as the function is continuous, because you have nothing to worry about in terms of discontinuity, holes, asymptotes, or domain restrictions. But if you do have those, then we have to be a little bit more cautious. So these first examples, you will not see, they will all be continuous, and that's the nice part. And then we'll go into some that are discontinuous and have some kind of restriction, and we could talk about those. So direct substitution just means that we substitute, or we plug in the value for the variable or variables, for if they're multiple, for instance, multiple x's in it, for the variables, put that in parentheses because you'd have multiple, into the function. And when you do this, you have you will get the limit. So for instance, in this first one, there is no discontinuity in a function like this because it is a there's no rational function. It's not piecewise. There's nothing to restrict an x value. Okay, so we could substitute 1 in for any of the x's that we see here. So here we will have 1 cubed plus 2 times the quantity of 1 minus 3. 1 cubed is 1 plus the 2 is 3. 1 minus 3 is negative 2, so negative 2 times 3 is a negative 6. And we could say the function, or the limit as x approaches 1 for this function is negative 6. Okay? Now, if you don't believe this, we could pull up the graph. And here we have this function. If you can see, it's written on that first line, x cubed plus 2 times x minus 3. We graph this. We zoom in around x is equal to 1. You could clearly see points in at about negative 6, and it is coming in from both the left and the right. It approaches negative 6. So that is how you know. That is one way you could just double check to make sure that this limit approaches negative 6 at x is equal to 1. Okay, so B, we could do the same thing. This is definitely going to be a continuous function. There's no domain restriction for this. So we have, for instance, negative 3 quantity squared minus 2 times negative 3 plus 4. Negative 3 squared, be careful, it's negative 3 times negative 3, which is 9. Negative 2 times negative 3 is a positive 6. And we add on that 4, which would then added up all together is equal to 19. So the function, or the limit, as x approaches negative 3 for this function is equal to 19. Oops, 19. Now here we do have a domain restriction because we could never have a radical that is negative. It would go into the complex realm. We don't want to do that. So we know that as long as this number plus this number does not equal a negative, we could do this. And if we think about it, the opposite of a positive 13 is a negative 13. That is where our domain would kind of just cut off. So that is the furthest left we could go is negative 13. If we notice also, we have a negative 4 here, which is greater than negative 13, so we could absolutely do this. When we plug this in, we get negative 4 plus 13 rooted, which is square root of 9, which is 3. So the limit as x approaches negative 4 is for this function is 3. We could do the same thing here. There is going to be a restriction here because we have a rational function. The restriction is that x cannot be equal to 5 because the moment we have that, we have a asymptote. So I should say an asymptote. So if we plug this in, as long as this value is not 5 and as long as it doesn't cancel out to create a hole, then we're in good shape. We plug in the 2, we end up with 2 plus 3 over 5 minus 2. 2 plus 3 is 5. 5 minus 2 is 3, so this is going to be equal, this is the limit as x approaches 2 for this function is equal to 5/3. Moving on. This one's an interesting one. Now, at any time that you want to just practice one on your own, you absolutely could. For instance, I would probably do it for F. But for E, let's take a closer look. There's no X here. So what do? Well, if you really think about this, this function is just y is equal to 5. And if I actually graph this, if I put 5 here, it'll be a horizontal line. Now, if we approach, for instance, 3 from both directions, the limit approaches 5 in both directions, from the left and the right. So no matter what on this graph or on this limit, the limit will be approaching 5. That will always be the case because there's nothing to substitute in. It is limit as x approaches 3 will be 5. It doesn't matter what the x is, it will always approach 5. If you want to give this a shot, pause the video, try this one out on your own. All right, so here it is. All you do is plug this in. You end up with 6 minus 3 squared. 6 minus 3 is 3, so we do that first, parentheses. Then we square, which is 9, so the limit as x approaches 6 for this function, is 9. All right. Now another one. There can be restrictions for trig functions. Sine and cosine do not have one, but tangents do because there are undefined moments for tangent. But luckily for us, sine does not. We just have to kind of realize, oh, okay, here's our unit circle, 0 pi, pi over 2, pi, 3 pi over 2, and then 2 pi. We know that pi is on this far left side, so we could consider, okay, where is our limit, or what's our value there as x approaches pi from the left and the right? Well, we know, so this is what we would do, sine of pi. We plug it in. We know sine of pi is going to be, this is the coordinate, -1, 0. Since sine is the y value, we're going to be concerned with the 0, and as x, and that's what this would be equal to, 0. So the limit as x approaches pi for sine of x is equal to 0. And we could see that with the graph because from the left and the right, or in this case, kind of like the top and the bottom, it approaches 0. Right. Now here is where it does get interesting. If direct substitution fails, or when it does, you want to follow these steps. Can you cancel out a common factor? For instance, like if you factor out something in the numerator and denominator and they work them to cancel out completely, then you would have whole. A whole would then mean that there is a domain restriction and we have to consider the limits from both sides. Same thing with this, we could simplify and cancel common factors, rationalize any denominators or numerators with conjugates, or even consider piecewise functions. Let's do this first one, and you'll see what I mean. When we plug in 2 here, we'll end up with 3 times 2 minus 6 all over 2 squared minus 4. 3 times 2 is 6. 6 minus 6 over 4 minus 4, which is equal to 0 over 0. We call this indeterminate. Indeterminate. When this happens, you're going to want to do one of these 4 things. These are the things you should consider. Can you factor this? Absolutely. You could take out a 3 from the numerator and you get x minus 2. You could factor out the denominator to be x plus 2 and x minus 2. The moment you do that, you realize, okay, we have values that cancel out here. If we graph this really quickly, if you put this on a graphing calculator, you will hopefully see that we'll have an asymptote here at positive 2, or so we'll have an asymptote at negative 2. We'll have a horizontal asymptote at 0. Probably have a function that kind of looks like this. But at the same time, we should have a whole when we have x is equal to 2 because of these that cancel out. There should be a whole somewhere about here. And we could determine what this value approaches by actually plugging in that value too. So what we're going to do here is we're going to rewrite this as 3 over x plus 2. When we plug this in, when we plug in this 2, we can actually calculate the limit. So I'm going to actually erase some of this just so we could, actually no, it's okay. Plug in that 2 and see what we get. Let's do this in a different color. We now have 3 over 2 plus 2, which is equal to 3 over 4. And that is what our limit will approach here. That is the y value. So let's say this is, for instance, 1 and 0.5. Halfway there would be 3/4. Okay? You do the same thing for b. If you want to give this one a shot, go ahead, pause the video. But here we go. You could factor it, well, right away you could say 0 because it's 0 squared, plus 0 all over 0 is going to be indeterminate. So we factor. When we factor out an x, and then we get 3x plus 1 all over x. X's cancel, and now we no longer get that indeterminate case. The moment we plug in a 0 here, we end up with 3 times 0 plus 1. 3's cancel out with the 0, or they just wash away, and this function's limit will be equal to 1. All right, pretty good. Last one. Here's another good one. This one you actually don't FOIL. You'll see what I mean in a second. The moment you plug this in, you end up with a 0 here. So you end up with 3 squared, which is 9. 9 minus 9 is equal to 0. And you have a 0 in your denominator, so this is an indeterminate case. But what happens here is you actually can't FOIL this. What you should do is actually, you can't factor it. You actually should FOIL it. So you should do 3 plus h times itself, 3 plus h. After you FOIL it, you should end up with 9 plus 3h plus 3h plus h squared. Bring down the minus 9, put this all over h, and now we can simplify. 9 and 9 cancel. 3h and 3h make 6h, but we should probably put the h squared in the front. So h squared plus 6h all over h. And if you notice, now we could factor out an h. So we end up with h times h plus 6 all over h. H's cancel, and now we have a new limit to actually calculate, or to work with. So the limit would be, if we plug in, since it's a 0, we could plug it in. We could do 0 plus 6, which is equal to 6. So here we would say the limit as h approaches 0 for this function, is 6. We are done. All right, so there is a homework posted on Shobi. If you do have any questions, please let me know, and I'll see you in the next one. Bye.